Now that we've discussed study level ratings, let's discuss how the WWC aggregates findings within a domain both within studies during an individual review and across studies for synthesis. Remember that the WWC calculates effect sizes to measure the magnitude of findings. The effect size represents the impact of the intervention in standard deviation units. Because the effect sizes provide a common scale for measuring impacts, they can be used to compare findings across different outcome measures. For the same reason, effect sizes allow the WWC to aggregate impacts across outcome measures and across studies for the purposes of summarizing the evidence. During the course of a study review, the WWC may calculate effect sizes at two different points. First, when assessing the magnitude of baseline differences between the intervention and comparison groups, and second, when calculating and reporting on the effects of the intervention. Finally, for domains with multiple findings, the WWC synthesizes effects at the domain level, which we will discuss in a little more detail shortly. Remember that the WWC not only calculates effect sizes, which indicate the magnitude and direction of an intervention effect, but the WWC also determines the statistical significance of findings. An effect is described as statistically significant when the measured difference in outcomes is unlikely to have been observed under the assumption that the intervention had no impact. The WWC follows a standard convention that labels a finding as statistically significant if the probability of observing an effect that is at least as large as the measured effect under the assumption that the intervention had no impact is less than 1 in 20 or 5%. Sometimes studies will report multiple main findings in the same outcome domain. If study authors report multiple main findings that meet WWC standards within an outcome domain, the WWC will compute a domain-level average effect size, and the WWC will calculate the statistical significance for that domain-level average effect size. To do this, the WWC uses a fixed effects meta-analysis approach to synthesize those findings into a domain-level average, and the WWC's presentation of the study results will focus on that domain-level average. The domain-level average receives the highest research rating that any individual finding received. Before we discuss aggregating multiple findings, we will note that when a study has only one main finding within an outcome domain, then that single main finding also will be reported as the domain-level finding. This slide shows the formulas that the WWC uses to aggregate multiple main findings in the same outcome domain in order to calculate the domain-level average effect size and its statistical significance. This approach calculates the simple, unweighted average of the effect sizes for the individual main findings within an outcome domain, as well as a standard error for the domain-level effect size that accounts for the average correlation between the outcome measures. This general formula is applicable to any of the effect size and standard error estimators described in Appendix E of the handbook, and so is appropriate for both individual level and cluster level assignment studies. The WWC then will determine the statistical significance of a domain-level finding by first computing the t-test ratio between the domain-level effect size and its standard error. To do this, the WWC uses the formula shown here. The degrees of freedom for determining the p-value for this t-statistic are based on averaging the degrees of freedom for the contributing main findings. The WWC uses the domain-level t-statistic and degrees of freedom to compute the domain-level p-value, If the p-value from a two-tailed t-test is less than 0.05, then the domain-level finding is statistically significant. No multiple comparison corrections are required because the domain-level finding is a single aggregate summarizing across multiple main findings within an outcome domain, adjusting for the average correlation among effect sizes. Let's consider an example where the WWC aggregates two main study findings that are in the same domain and that meet standards. Say we have findings for two different math achievement measures. The first math achievement measure has an effect size of 0.446 and a standard error of 0.153. The second math achievement measure has an effect size of 0.348 and a standard error of 0.142. Using the formulas shown on the previous slides, we first can calculate the simple average of the two effect sizes. This domain-level effect size is equal to 0.397, and the domain-level standard error then is calculated as 0.136. The WWC then could use these results to calculate the statistical significance of the domain-level finding. The WWC also will use a fixed effect meta-analysis approach to combine findings across subsamples for a single outcome measure within a study. Studies often will present findings separately for several subsamples of participants without presenting an aggregate result that combines findings across all of those subsamples. For example, study authors may present results separately for students in 6th grade, 7th grade, and 8th grade, but they don't report findings for the full sample of 6th through 8th graders. In these scenarios, the WWC may query authors to learn whether they conducted an analysis on the full sample. The study author's analysis is preferred since it may be more precise than the WWC's computation. If the WWC cannot obtain aggregate results from the author, then the WWC averages results across subsamples for a single outcome measure within a study. The WWC only will aggregate across subsamples for a single outcome measure within a study if the subsample findings meet the following criteria. First, the subsample findings must be independent or non-overlapping. Second, the subsample findings must have the same outcome measure. Third, the subsample findings must have the same follow-up period. Fourth, the subsample findings must have used the same outcome scoring procedures. And finally, unadjusted or adjusted means must be reported. For more detailed information about the formulas used for aggregating these findings, see Appendix F in the handbook. This slide shows the formulas the WWC uses to conduct a fixed effect meta-analysis to aggregate findings across studies within an outcome domain in order to inform effectiveness ratings. The WWC combines the domain-level averages for a given domain across all the studies in a synthesis. This meta-analytic approach gives more weight to studies with more precisely estimated effects. For example, a simple randomized controlled trial, or RCT, with 300 participants would have approximately 3 times the weight of another similar trial with only 100 students. This is achieved through the use of inverse variance weighting, where effect sizes are weighted by the inverse of their variances when the mean effect size is calculated. These variances are largely determined by sample size and design and are the square of the standard error. Appendix F contains additional details about the formulas used in fixed effects meta-analysis. Let us walk through an example. Imagine the WWC is conducting an intervention report examining the effects of a specific math intervention on students' math achievement outcomes. Let's say there were 3 RCTs that all had study-level research ratings of meets WWC standards without reservations. These 3 studies all reporting findings for outcomes in the math achievement domain. This table shows the domain-level effect size and standard error for each study. For instance, the first study had a domain-level effect of 0.397, the second study was 0.413, and the third study was 0.156. And each of these studies varied in the precision with which they were able to estimate these intervention effects. For example, the third study had the smallest standard error value of 0.054. This smaller standard error means that the effect size in the third study was more precisely estimated than the effect sizes in the first or second study. This is likely a reflection of sample size, such that the third study likely had a larger sample size than the other 2 studies. For this reason, the third study receives more meta-analytic weight in the model, since it provides a more precise estimate of the intervention effect. Using the equations shown on previous slides, the meta-analytic average then can be calculated as 0.205 with a standard error of 0.048. These findings then can be used to assess whether the meta-analytic average is statistically significant or not. One important side note is that in some instances, the WWC may reweigh the fixed effects meta-analytic synthesis to constrain the bias from findings that meet WWC standards with reservations. Additional details about these reweighting procedures are provided in Appendix F of the handbook. In the next chapter of this module, we will discuss determining effectiveness ratings.